Hello and welcome to Section 10. We'll be discussing the giant planets and all their great, amazing detail. And the range of topics that we're going to be discussing is things like, what are storms like on a planet like Saturn? A planet that's entirely composed of a gaseous atmosphere. What kind of patterns in the wind speeds? How will storms rotate around these planets? These are things of our discussion topics today. As usual, at the beginning of a new section, let's dive into a reading quiz. We'll ask ourselves what are the giant planets primarily composed of? So, go ahead and pause. Be right back. This one should be a very straightforward one. It's going to be a lot of molecular hydrogen and helium, and this just goes down to the abundance. Where the giant planets form is predominantly a hydrogen gas. Now, by molecular hydrogen, we're just talking about hydrogen that's been squeezed enough that you're having a hydrogen atom bond with another hydrogen atom. So you have these molecular H2 floating around. Over the next few videos, we're going to describe the properties of the giant planets and go into a little bit more detail, just break them out into categories of the gas giants versus the ice giants. And from there, we'll then talk about the atmospheres on all four of the giant planets in our solar system and their corresponding magnetic fields, how they're produced as you go through the layers of the planets. At the very end, we'll briefly discuss things like these super or hot Jupiters. And this is an artist's depiction of Kappa Andromeda b. And it's a gigantic reddish planet close to its star that it's orbiting outside of our solar system. Now, what is the origin of the giant planets? Like we said, we have two distinct categories that will break them down. The gas giants formed around the protoplanetary accretion disk. Remember back to our previous sections, we talked about the great nebulous that eventually would collapse down with the protostar at the center and a accretion disk around the edges of this protostar. The gas giants would have formed inside that, and that's why they're predominantly hydrogen and helium. Now, the ice giants, a little bit further out, those were later formed by basically small ice bodies merging together, gravitational attractions smacking together and globbing together enough to form the giant planets there. Now, when it comes to discussing the giant planets, all four will possess a dense liquid core and some rocky materials down there. But don't be mistaken to think that there's like the surface that you ever could land on when it comes to the giant planets. And one thing they'll emphasize throughout these sections, throughout these videos, is that there are a lot of details that we still don't fully understand. Instead of asking how long ago the planets formed, you can instead ask, how long have we as humans known about them? When it comes to Jupiter and Saturn, we've known them as old as the ancients. Remember back to how you define a planet. You would look at the stars, and you would see the bright objects, and some of them would do that retrograde motion. They'd have their normal prograde motion, and they'd start to retrograde. So anytime that you saw that happening, that was the definition of a planet for the ancients. And so Jupiter and Saturn, they met those definitions. Uranus was too faint. We just couldn't quite distinguish it from the stars. So it wasn't really until the invention of telescopes yet Uranus was able to be plucked out and say, oh look, there's another planet in our solar system. It was actually discovered in 1781 by a man named Herschel, who actually mistook it to be a comet in the background, a slow-moving comet. Once we knew about Uranus, we started to try and map where it was going to be. Where was Uranus in the night sky? And people found that Uranus wasn't where it was supposed to be. And what they realized was that Neptune was out there, giving these gravitational tugs on this. Now, the discovery of Neptune is accredited to both mathematicians, a French one, Urbain Le Verrier, and I'm sorry if I'm butchering that pronunciation, and an Englishman, John Couch Adams. They were looking at the orbits of Uranus through the night sky, and they're doing these calculations called perturbation theory. Think of it as you've got your normal gravitational tugs, Sun on Uranus, and now add the complexity of, say, what we now know to be Neptune. Neptune adds a little tug, and even though the gravitational force of the sun on Uranus is the biggest factor, you still have these little tugs, and you apply this perturbation theory to explain the little tugs. It's a mathematically difficult but solvable problem. And so you start calculating all these little tugs, all these little perturbations. And with that, both these people independently predicted the existence of Neptune. Once they'd published their work, a man named Gale in 1846 immediately looked out to where the predictions, the mathematics said, hey, there should be this other object out there, and that was the discovery of Neptune. So the gas giants will be our Jupiter and Saturn, and the ice giants, Uranus and Neptune. Coming back to our gas giants, they're what we said before, this predominantly hydrogen helium. In some regards, we think of Jupiter as being a failed star. It wasn't quite massive enough, but its chemistry is going to be very similar to what you see on the sun. Lots of hydrogen bubbling around. Now jumping over the ice giants, the reason we call them ice giants is because the materials that you find on them, methanes, ammonias, waters, here on Earth, those would be in a liquid state. But because of how cold, how distant these planets are, these will turn into these icy materials. You'll have clouds of methane and ammonia on these two planets, the ice giants. The picture we have displayed here is an example of stellar occultation, and this is an example using Pluto, and we'll save a detailed discussion about Pluto in a later section, but the premise, the principle that we're showing here, the stellar occultation, matters. So these are two separate dates, right? You've got the 18th of July and then the 19th of July down here, and here's what's going on. You've got a star, Nomad 1, crazy set of digits, right? And you see Pluto's path. This is, remember, its apparent path because of where we live on Earth. So Pluto's apparent path in about 24 hours from now is going to move, and block star Nomad 1. So in a day later, Pluto has moved, and at that point in time, you can't see the star behind Pluto. That's stellar occultation. And this is going to be a very powerful trick that we're going to use when studying the giant planets. Let's use the stellar occultation and we'll measure the size of the giant planets. Here's the principle, right? Off and to the right, you'll have the stellar light coming in, right? So each ray here refers to a different timestamp. And we're going to be on good old happy Earth watching a star in the distant background. So at the first timestamp here, you can just see the star, right? You can just see the star on the edge of the giant planet. Well, as Earth moves, as the apparent position of the planet shifts, eventually the star will be blocked. We'll no longer see it. It's been going through this stellar occultation. Now wait a little bit more time, and eventually now you can see the star on the other side of the planet. So, basic principle. Distance is your velocity times time, your speed, and the time that it travels. We have a pretty good idea of how fast Earth is moving, right? Its orbit around the sun. So all you need is this timestamp. How much time transpired from seeing the star on one side of the planet to seeing the star on the other side of the planet? How long was that star stellarly occulted by the planet? And with that, you can get the size of the planet, how big that planet is. Now, if you want to ask questions about, say, the masses of the planets, well, you're going to need tricks like observing a moon orbiting around the planet. Remember Kepler's laws. You need to have a satellite orbiting around the planet. And if you have the distance of the satellite and how quickly, or specifically the period of the satellite to go around the planet, that will get you the mass of the planet itself. So before we get into detail explicitly about each of the individual giant planets of our solar system, let's just lay out some final characteristics. Planets like Saturn is less dense than water. If I was to take a scoop of Saturn and put it in a tub of water, it would float. Though it does have some heavy elements present Overall, Saturn's chemistry is very much like Jupiter, whereas Uranus and Neptune do have an abundance of heavier elements. But the last characteristic that we're really going to focus on here is this oblateness property, and that's what this figure is trying to show. So here's this principle. You take a planet and you start rotating around. Let that planet rotate. Now, because of how loosely dense these, remember, are mostly giant gas clouds, because of the rotation, the planet will oblate or flatten out. And this is a characteristic we see with all the gas giants. Technically, you do see it with the terrestrials too, but it's just not as apparent.